Hi guys, my name is Mr. Lead and today we're going to be talking about sound. Now previously we've discussed how sound is a form of energy. Now like sound, there are some forms of energy that come in a particular form, and that form is waves. Some energy comes as waves. Light travels as waves. Heat sometimes travels as waves. Electromagnetic radiation, that travels as waves as well. Sometimes kinetic energy can even travel as waves. You see this in earthquakes where the ground moves as waves, and even in tides as the ocean comes back and forth in waves. Sound is another form of energy that comes in waves. Now, when we talk about waves, we'll discuss more of what waves actually look like. But before we understand how a wave works, we first got to understand how sound basically works. What sound is it's just the vibration of particles in a substance. So when I'm producing sound here from my mouth, I'm causing the air molecules here to vibrate, which causes air molecules here to vibrate, which causes air molecules here to vibrate, which causes these to vibrate, and so on and so on and so on. It's the passing on of these vibrations. That's what sound is. Now, what's really important to know here is that when I'm causing sound, I'm not sending particles your way. I'm not moving these particles along. All these particles are staying in roughly the same place, and each of these particles are just vibrating a bit, which causes their neighbors to vibrate. So this movement is kind of more, instead of this movement being like someone running across a football field, it's more like all these particles are staying in the same place and doing little Mexican waves. That's how you can kind of think sound to be. Now, that's the way sound works. Sound can travel, like other ways, sound can travel in two different ways. It can travel as transverse waves or longitudinal waves. I've got a little animation to help further explain these two. Now, keep in mind that these are all some sort of particle. All of these particles are staying in roughly the same place, but the difference between a transverse wave and a longitudinal wave is the way that these particles vibrate. In a transverse wave, we see the particles moving up and down, and that creates a very common sort of wave, the type of wave we're more used to. And what you'll note, remember, these particles are not moving along, and this first particle is not now going to end up over here. It's going to end up in the same place it started in. Longitudinal waves, again, they end up in the same place they started in, but instead of moving up and down, a longitudinal wave will see particles moving back and forth like this. So these are the two different ways that waves can travel. All right, and in the way sound works, sound will travel as either longitudinal waves or transverse waves. More specifically, sound will only ever travel as transverse waves in solids. So you'll only ever see this in a solid. However, longitudinal waves is the way that sound travels in air and in water and also in solids. You'll see more commonly sound traveling as longitudinal waves like this. Also model this sort of movement with a slinky. So a transverse wave, we'll see the springs of the slinky moving up and down like this. And note, every single spring stays in the same place it is after the wave has finished moving. In a longitudinal wave, we'll see these springs moving back and forth. Like that. And that is how sound travels. Because sound just consists of vibrating particles, the source of sound has to be some sort of object that vibrates. For example, when I clap, that clap creates some vibrations. My hands there are vibrating against each other, which causes the sound around the air particles around it to vibrate, which gives us the sound that we hear. When I speak, my vocal cords are vibrating. And so when air passes through them, the vocal cords are causing the air particles to vibrate, which creates, again, the sound that you hear. Now, when sound travels through a medium, it will often collide with different surfaces. And depending on the surface, sound can react in different ways. It can either be reflected by a surface, absorbed, or diffused. We'll look at each one of these. So reflection. This often happens with hard surfaces. If sound is traveling and it hits a brick wall, that brick wall is going to reflect most of that sound back and cause the particles to vibrate in the opposite direction. And so this is actually why we hear echoes. In say, a large cavern or something, the walls of that cavern is so hard that the sound waves are just reflected off the walls and end up coming back to your own ear. Absorption, on the other hand, is when this often happens mainly with soft surfaces. Absorption is when a surface literally absorbs the sound. So if you're in a room and the walls are really fluffy, you'll notice that you'll never get an echo because the sound is always absorbed. This is a place where most voice recording happens. You have to have a really soft-walled room so that the sound can be absorbed. By the way, the science of studying the way that sound moves is called acoustics. There are certain scientists who have a very smart understanding of how sound moves of different sort of surfaces and how they can be bounced off different angles. And so if you're very smart with acoustics, you'll know how to get diffusion to work. Diffusion is the most complicated way that sound can react with a surface. We're not going to delve too much into diffusion because, like I said, it's very complicated. But basically, if you have a very bumpy surface, a rough surface, you can get the sound to scatter. And this doesn't really cause an echo. It will just mean that when the sound scatters, you don't get to know where the origin of the sound is. It doesn't sound like it's coming from any one place. And this is actually, again, sound booths usually try to utilize absorption so you don't hear echoes, but very professional sound booths will have walls fitted like this to try and get that act of diffusion happening. So not only do you not hear an echo, you don't even know where the sound is coming from. Now, sound can travel at different speeds through different types of mediums. We got three different states of matter: solids, liquids, and gases. Sound will travel faster through a medium that is more dense. So with that in mind, we're so used to hearing sound in a gas because our eardrums, the thing that picks up sound, our eardrums are just connected to or just exposed to the open air, which is a gas. But if you go underwater, you'll actually find that sound travels faster in water because it's a higher density. And sound even travels faster in a solid because it's even more dense. Now, you might be wondering, hang on, so if sound travels faster in a solid, how come I can be in one room and someone can be in another room and they can't hear what I'm saying? Well, what you got to remember is that sound doesn't like to really move between two mediums. And so if sound is created in a gas, it's going to have a hard time transferring through into a solid. But the reason why you can knock on a wall and that can easily be heard next door is because that sound you're creating is made on that solid, and that sound travels easily through that solid. Okay, now we're going to look at the different dimensions that sound consists of. So you'll notice that sound can have a higher pitch and sound can also have a lower pitch. And the reason for this is because of the wavelengths of sound. What is a wavelength? Well, when we see a wave moving up and down, one wavelength is the measure of distance between that full particle's movement. So if we're looking at transverse waves here, a wavelength is just the measure from a peak to another peak. All right. So this is one wavelength here, and so here on this little diagram here we have 1, 2.5 wavelengths. All right. So the more wavelengths you have in a given amount of time, so the more wavelengths you have in a second, the higher pitch something is going to be. So right if you were to look at the air molecules of the sound that I'm producing, the wavelengths are actually really, really close together.
But right now, you would see the wavelengths being really spread apart.
So yeah, that's how we measure the pitch of a sound. It's determined by the wavelengths. Now, the second dimension we're going to talk about sound is volume. If we're looking at a transverse wave, the volume is also known as the amplitude. The amplitude is measured by how high this peak is from the molecule's resting position. If it's a really high peak, if the molecule is moving a greater distance, that means that that molecule has more energy, and therefore the sound is going to be louder. But if the amplitude is lower, then the molecule hasn't got as much energy, and the sound is going to be quieter. So we can see this here. Higher amplitude means it's going to be louder. Lower amplitude means it's going to be quieter. Now, remember how I said most sound travels as longitudinal waves, and that's still true. But when we represent sound on a screen or in a drawing, we usually represent it in transverse waves, because that's a bit easier to depict. But if you're wanting to know how sound looks in longitudinal waves, you don't really need to know this, but if sound has a higher amplitude, we're going to see these compressions really closer together, and the refractions being really spread apart. But if it's got a lower amplitude and it's going to be softer, the compressions and refractions won't be as distinct. Okay. All right, the last thing we're going to learn about is this process called resonance. Now, to understand resonance, you also need to understand that every object has what's called a natural frequency, a natural way that they will generally vibrate. So this glass, for example, if I ping it, you will hear its natural frequency, and that frequency we can represent with a certain type of wavelength. The frequency is how many wavelengths go past in a certain given amount of time. Now, when we talk about natural frequencies, you can create vibrations to move a certain object at that natural frequency. And if you do that, and if you keep that at a high enough amplitude with enough power and at a consistent enough amount of time, you get what's called resonance. And resonance can be quite destructive. So a better way to understand resonance is if we relate it in an analogy, if we relate it with a swing. So depending on a swing's length, every swing will have a natural frequency. And that natural frequency is how frequently you are supposed to push someone on that swing to make them go forward. So this man is pushing this girl at the right amount of times. That's the right natural frequency. But if he was moving his hands too fast and he was pushing too fast, then the girl wouldn't move, would she? And if he was pushing too slow and waited at the wrong points, then that means that he wouldn't actually hit the girl at the right times to make her push up and down. So he is pushing the girl at the swing's natural frequency. And if you push this swing at its natural frequency enough times, then that will mean that the swing will go back and forth further and further and further and further. This is how sound works. And so this is how an object can resonate. A very common example is a glass, a wine glass. You can see, you can actually break wine glasses with your voice if you match the natural frequency that it produces. So if you sing at a wine glass at at the same pitch as its natural frequency, and if you sing it at it with enough power, i.e. enough volume, then you can break that wine glass. But resonance can be even more destructive than that. A classic example is the Tacoma Bridge. This bridge was actually destroyed by air particles, and the wind actually moved on this bridge at a strong enough rate to cause it to collapse. Now, this was back in 1940. You can look it up. And since then, architects have been much smarter with the designs of their bridges. A couple more things to note. Frequencies and amplitudes have different ranges. Us humans, our eardrums are only designed to pick up ranges of frequencies at a certain rate. If the frequencies are too high, then our eardrums aren't actually going to be able to pick it up. Same if it's too low. Dogs are actually better at picking up high frequencies than us humans. That's why dogs can hear dog whistles. High frequencies can also be used in medicine, and as well, they're often used by bats. Now, as well as frequencies having a range, amplitude has a range. We measure the range of frequencies with hertz. We measure the range of amplitude, or the volume, with decibels. So if something is really, really loud, that actually can have a destructive effect on our hearing. 1 in 5 teens actually suffer from some sort of degree of hearing loss because they actually expose themselves to the 110 decibels that are given off by the maximum volume that comes from your headphones. These things can be really dangerous if you're listening to them too loud. So that's why we've got to be really careful with what sort of sounds we're exposing ourselves to. Now, before I go, I'm just going to leave you with this one final little note. No pun intended. There is actually a disease called synesthesia. And synesthesia is a disease where someone can actually see sound and they can actually see music. It's a psychological disease, and when they hear certain sounds, they see different types of colors. 1 in 1 million people have it. Jeffrey Rush here actually has it. I'll go let you look that up and do your own sort of investigations. But for now, thanks for watching.